All right, hello everyone, and welcome to the last lab of Qubit by Qubit's Intro to Quantum Computing course, semester 1. So today we're going to be continuing last week's topics on the mathematics for quantum computing, diving into a couple of new concepts, doing a bit of review from last time, and really sort of setting up a preview for what semester 2 will hold. We have quite a bit of content to cover today. I know I feel like I say that pretty much every week, but hopefully we can take it slowly. Again, I'll do reviews of everything before we do examples and hopefully make things a little bit clearer. Quick look at our program for today. We'll start off just with a brief note on course logistics. Actually, I'm not sure if we have that today. Okay, well, I believe that's just an error in the agenda. There's no logistics. We'll just start off immediately with the attendance quiz. After the attendance quiz, we'll do our pre-lab Zoom feedback, questions from last week, lab content, and post-lab feedback. Questions from last week, again, we didn't have any prepared based on what we saw on Piazza and elsewhere. So if you do have any questions that you had from last week's content, get those ready. I'll just be opening up the chat at that time to answer one or two questions from last week's content before we move on to this week's content. So let's launch right into the Canvas attendance quiz as usual. We are in lab 2A. The quiz password this week is 3222. That is 3222. So today's question is, if you have not attended the Friday student assistant office hours, why not? And I guess there's a bunch of options in there on Canvas that you can select from. As usual, the quiz is not graded. There's no correct answer. We just want your honest response on this question. It'll help us gauge things for how we run semester 2. But please make sure you do fill out that attendance quiz because that is how we get your attendance. As usual, I will give about 30 seconds or so here for everyone to fill out the Canvas attendance quiz, and then we will get going shortly after that. Okay, let's get going. So we'll start off with the pre-lab Zoom feedback. You should be seeing that pop up on your screen pretty shortly here. So let me know how you felt about this week's content, if it generally felt easy or not. And again, I'll use this to help gauge how fast we go through things this week. And then as people are still filling that out, the next part of this is going to be questions from last week. So I'll go ahead and open up the chat. If anybody does have questions from last week's homework, last week's content, whatever, feel free to throw those in the chat and I will take some time to answer one or two of them before we move on with this week's content. So once again, if you do have any questions from last week, feel free to throw those in the chat and I will do my best to answer them. Okay, number 16. Would you mind either copying it into the chat or giving me a short description of what it was? I should probably just have the homework open in front of me. That'll be an improvement for next semester. Awesome, thank you. If you missed last week's lab, I would strongly recommend you go back and watch it, especially, so this week's lab is going to build on a lot of the content from last week. So we'll be, again, dealing with vectors and matrices and introducing some new concepts with those. Okay, so one person asks, how do you do the inner product of plus and minus or any problem similar to this? Great question. So the inner product of plus and minus is written like this. And in our last lab, so we did cover a question similar to this in last week's lab. It might have been in the optional content. I actually don't quite remember if it was in the required or the optional content. But the tricky thing about this is that both of these, plus and minus, are superpositions. So we're used to using the inner product formula on things that are just written as vectors. And then you can take sort of like V1, V2, W1, W2, and use the inner product formula. So here, what you would do is you would start off by writing plus, for example, which is probably given to you as something that looks like this. And we'll be seeing this again quite a bit today. And minus looks like this. Minus 1/√2. There we go. So the first step in solving an inner product like this is always to write these two things as column vectors. So you can go back and look at that lab if you need a refresher on how to do this, but these two vectors would end up looking like this. Sorry, my pen is being funny here. You would end up writing them like this. So you convert them to column vectors, and then you would just go ahead and label these as usual. So your top one here would be V1, V2, W1, and W2. And then you would go ahead and just plug these into the formula for inner product. So all that stuff was covered last week. We're actually not really going to touch inner product too much today. So if that didn't make total sense, feel free to go back and watch last week's lab again after this lab. The concept of span, yes, we will get to that today, absolutely. And then what is the probability of, okay, so I'll do one more question. The probability of measuring psi in the 0 state. So there was a piece from last lecture where we learned that the probability was given by the modulus squared of the coefficient on the state you're measuring. So that was a very confusing bunch of words. I will write something down. So if you're given phi, just some random state, written as a superposition of 0 and 1. So for example, it might be written as alpha 0 plus beta 1. Alpha and beta are just some numbers. They might be complex. The probability of measuring phi in the 0 state is given by the modulus of alpha squared. So for example, if alpha was, I don't know, say minus I/√2, if that was the coefficient on ket 0, then the probability of measuring 0 would be the modulus of that squared. And then you can go back to the some of our first lectures on complex numbers to find how you would take the modulus of this. But it turns out just to be 1/√2. And I guess I don't need the modulus anymore. I already took the modulus. It's equal to that squared. And then, so the probability of measuring this in the state 0 would just be 1/2. And so once again, that stuff with figuring out the probabilities of measuring in certain states, that was also covered last week in both the required and the optional content. So there were lots of examples in last week's lab as well, if you still want to watch some more of that. Okay, so for anybody asking about the attendance quiz, we did do the attendance quiz already. The quiz passcode is in the lower right of the screen, as always, so you can go ahead and use that to fill out your attendance. And yes, this is the last session of the semester, believe it or not. So after this, we go on a, oh gosh, I actually don't know if it's a 2-week or a 3-week break. But yeah, we go on a break after this for the holidays. And then we will see everybody, 2-week break, thank you. Then we'll see everybody back here in January when we start semester 2, which there's a lot of very exciting stuff. Basically, the structure of this course, if this hasn't been said already, the first semester is a lot of sort of kind of scattered and sometimes unconnected or seemingly unconnected mathematics that we're teaching you, but all of it is in preparation basically for semester 2. Semester 2 is when we get into really what I would call quantum computing fundamentals. But in order to do that, you need all of this background on linear algebra and probability, all the stuff that we've been teaching you so far this semester. Okay, cool. Well, thank you for sending in those questions. I am going to move on to this week's content. So we basically have two main parts today. The first is going to be understanding vector spaces and their properties. So vector space is a scary sounding word, but I promise it's a very simple concept. And actually, that's going to be a theme throughout this entire lab. I'm going to be throwing a lot of new terms at you. And I'm just going to ask you to trust that you should not be scared by these new terms. There's a lot of weird things you can see here, like eigenvalues, eigenvectors, span, linear independence, whatever. All of these are probably new words, or maybe you've just heard them during the lecture for the first time, but they're really not that complicated as concepts. You've already seen a lot of them. We just haven't used these names to describe them. So hopefully I can give you a more intuitive understanding for what they mean, because oftentimes this stuff is just introduced with a bunch of math and it can be really confusing. It's really not though. All of these are straightforward ideas if you understand sort of the gist of it. So we'll talk about vector spaces, linear combinations, linear independence, span, and basis vectors. So span was mentioned as one thing I will spend a bit more time on. And then the second half is all dedicated to eigenvalues and eigenvectors. So this is going to be talking about what they are, and most importantly, why we care about them. And this is effectively going to be the justification for why we look at linear combinations in the first place. It all has to do with eigenvectors. So hopefully by the end of today, a lot of the more obscure and seemingly random pieces of linear algebra that we've taught will start to make a bit more sense. The optional content is going to be a little bit of fun for me, basically. I'll be taking 10 minutes at the end of the required content today to talk a little bit about my research. So of course, this is totally optional. You can leave after the required content as always, if you would like. But yeah, I'll spend just a bit of time today going over my research. The cool thing is that with the content we've covered, it is perfectly understandable for this audience. So I'll spend a bit of time talking about that. All right, let's get into things. So everything in this lecture or in this lab is going to be structured around this analogy of getting donuts. So we start off on this map, which is the same map that we saw, I think, last week. And so say that we live here. Our home is located at the intersection of Cedar Street and Highland Avenue. And suppose we want to get donuts at this place over here called Davis Square Donuts. Now, obviously, the most direct way to get here is a vector that goes straight from our home to the donuts. It's a straight line. Now, as you can see from the map, though, there's no road that actually does that. There is not a single street that just connects our house to Davis Square Donuts. So instead, we have to not take the direct route. We'll take a couple of side routes. Here's one path we could go. We could first walk up Highland Avenue and then go down this little side street to get to the donuts. Or we don't have to do that. We could also have gone down Cedar Street first and then gone up Elm Street to get to the same place. So I realize this is all fairly simple, but you might recognize just from the way that we're drawing this, all of these things are effectively summing vectors. So this blue vector in the middle here is our target. That's what we want to get to. And both of these other combinations that I showed are just addition of vectors. So if you remember back when we talked about linear algebra, and that was a couple of weeks ago now, we said that the graphical way of adding two vectors was to draw them, first draw one arrow and then keep your pen at the end of that arrow, draw the second one, keep your pen at the end, and so on. So all we're doing here is we're adding vectors to get this blue vector. So some key takeaways. Number one, this blue vector is sort of broken down into a sum of vectors. Now, this is a linear combination, as I'm sure many of you might have guessed by now, but just to start getting you used to this analogy, the blue vector is broken down into the sum of vectors, which lets us follow the streets that are already on the map. Second point, there are multiple ways of summing to the blue vector. So as we've just shown here, there's two different sets of streets we could take to get to the same location. And in fact, there are probably many more that I didn't draw in here. The third key idea is that the vectors we sum must be in different directions. So notice how when I went up Highland and down the side street, there was always a turn. involved, right? Or when I went down Cedar and up Elm Street, I had to turn. So what would not have worked, as an example, is if I said, try and get to the donut place by only going up and down Cedar Street. That clearly, just by looking at this, you can tell that doesn't work because there's no way of getting to the donut place if you only ever go on Cedar Street. So the general way of saying this is that the vectors we sum must be in different directions for this to work. So we're going to go through these one by one, actually a little bit out of order. We'll start with the first one here, and then we'll do the third one. And then finally, we'll talk about this second point in a little bit more detail. So let's start off with the idea of breaking down a vector into a sum of vectors. As I alluded to before, this is what we've been teaching as linear combinations. So a linear combination is just a fancy word for a sum of vectors. We've already seen a bunch of different examples of linear combinations. So the plus and minus states, for example, which I briefly went over in the questions from last week, both of these are linear combinations because they're both sums of vectors. That's all it means. And so if we draw a general state psi as just alpha 0 plus beta 1, again, it's just a sum of vectors, and so we call it a linear combination. So let's do a little bit of practice. First of all, we're asked, write the state 3/5 minus 4/5 as a combination, a linear combination of ket 0 and ket 1. So again, what I like to do is every time I see this word linear combination, I literally will just, in my head or on paper, cross it out and say sum. Write this state as a sum of ket 0 and ket 1. Okay, let's go ahead and do that. So I want to write 3/5 minus 4/5. That's my starting vector. And I want to write that as sum, say alpha ket 0 plus beta ket 1. So again, these alpha and beta are just any random coefficients. And then ket 0 and ket 1 are the things I'm trying to write it as a combination of. So let me go ahead and substitute in the definitions of ket 0 and ket 1. So we have alpha 1, 0 plus beta 0, 1. And then I'll just move these coefficients inside of the vectors. So this one becomes alpha 0 plus 0 beta. And then last step, we know with vector addition, you just add the first row and add the second row. So this thing is going to be equal to alpha beta. So if we now look at what we've gotten to here, we have that 3/5 minus 4/5 should be equal to alpha beta. And so we can write this down as two separate equations. Our first equation is that 3/5 must be equal to alpha. So I'm just looking at the top elements of these vectors must match. And then the second equation is that the bottom must match. So minus 4/5 has to be equal to beta. Now, in this case, there's no further work done. We have actually just solved for alpha and beta. So my final answer here would be 3/5 minus 4/5 is equal to, and remember what I started with was this formula here. So it's just going to be 3/5 ket 0 minus 4/5 ket 1. And that's it. We have successfully written this state as a sum of ket 0 and ket 1. Now, for a lot of people, it helps to look at the graphical version of this. So here we have our XY plane. And in fact, we can label this a bit differently. You can think of it as the ket 0, ket 1 plane, like that. And this red vector here is what we're going for. It's 3/5 on the X direction, minus 4/5 in the Y direction. And you can kind of just see that this component, the component in the 0 direction, is 3/5. And then the component in the Y direction, or the ket 1 direction, is minus 4/5. So this is fairly easy to see when you're dealing with ket 0 and ket 1. But what about if we ask you to write the same state as a combination of something a little bit different? So for example, ket plus and ket minus. Now, this does look a little bit harder at first glance, but we're just going to follow the exact same strategy. So I'll start off. What do I want to do? I want to write 3/5 minus 4/5 as the sum of these two things. So again, I'm going to have alpha ket plus beta ket minus. Okay, and now just like before, I will substitute in my definitions of ket plus and ket minus. So here we have alpha 1 over root 2, 1, 1, plus beta 1 over root 2, 1 minus 1. Just like that. And now I'm going to try and do vector addition here. So I'll first move all of our coefficients inside the vectors. So we have alpha over root 2, alpha over root 2, plus, and here we'll have beta over root 2 and minus beta over root 2. Okay, and then vector addition. We'll get alpha plus beta over root 2 on the top, and alpha minus beta over root 2 on the bottom. So all those steps there is just linear algebra, addition, and multiplication of vectors. Now, once we are here, we can derive two equations from this. The top elements have to match, and the bottom elements have to match. So let's go ahead and write those down. The top elements have to match. So 3/5 has to equal, I'll write it this way, alpha plus beta over root 2. And second, the bottom elements have to match. So minus 4/5 has to equal alpha minus beta over root 2. Just like that. Now we have a system, two equations, two variables, and there's a bunch of different ways we can solve this. You are welcome to use whatever method that you want. I'm going to show just using substitution though. And how that works is I'm going to start off with equation 1. I'll solve it for alpha, and then I'll substitute that into equation 2. We'll get a value for beta, and then we'll go back and plug it in and get a value for alpha. So hopefully this mathematical procedure here, once you have these two equations, hopefully it's fairly familiar to go and solve for these two unknowns. So starting off with equation 1, we have 3/5 equals alpha plus beta over root 2. And so we have 3 root 2 over 5, just multiplying both sides by root 2, alpha plus beta. And then we can say that alpha equals 3 root 2 over 5 minus beta. So all this stuff is really just mechanics. You just have to work through it. It kind of is annoying, but it's just math. So now I will go ahead and plug this into my second equation. So we have minus 4/5 equals alpha minus beta over root 2. And so I'll plug in my value of alpha here. So alpha is 3 root 2 over 5 minus beta. Then we have again minus beta over root 2. Okay, so just solving this. Sorry, I know this is really tedious. Equals 3 root 2 over 5 minus 2 beta. Okay, and now what I want to do here is I want to ultimately solve for beta because we only have one unknown. So we have 2 beta is going to be equal to 3 root 2 over 5 plus 4 root 2 over 5, hoping I didn't make any mistakes here. And that is just equal to 7 root 2 over 5. And so then I'll bring this up, and we get beta equals 7 root 2 over 10. So all of that was just mathematical manipulation. And then my final step is to plug this value of beta into my equation for alpha over here. So we get alpha equals 3 root 2 over 5 minus beta is 7 root 2 over 10. So this is the same as 6 root 2 over 10 minus 7 root 2 over 10. And so we get minus root 2 over 10. Finally, so I know that was a lot more work than the previous slide, But now that we have alpha and beta, we're done the problem. So returning back to what we originally wanted to do, we originally wanted this equation right here. And that's what we got. We have 3/5 minus 4/5 equals, now my value of alpha is minus √2/10, ket plus, and my value of beta is 7 √2/10, ket minus. And that's our final answer. So again, all we're doing here is we've written our vector as a sum of these other two vectors. So I know that it took a while to get through, but again, the basic process is fairly straightforward. There's just a lot of kind of annoying math and manipulation. You have to be careful not to get it wrong. Okay, so I want to show a graphical representation here. So I'm just gonna remove some of my work so we can see it more clearly. Hopefully that's enough. Sort of, okay. So again, what we have here is our XY plane. And again, these axes are still ket 0 and ket 1. But now we have the same red vector. Instead of writing it as a sum on the X and Y axes, we're now writing it as a sum of plus and minus. And if you actually work out where these vectors are, plus and minus are roughly there and there. And so that's why we have one arrow going in this direction and one arrow going in that direction. So visually, all we're doing here is sort of defining two directions and then figuring out how much you multiply those directions by to end up with a target vector. So let's do one last example of writing linear combinations. Same thing, we're asked to write this state as a linear combination, or again, just a sum of these two states. So let's go ahead and do that. I'll start off with my state 3/5 minus 4/5 equals, and then we'll have a linear combination of these two. So alpha 1/√2, 1, 1, plus beta 1/√8, minus 2, minus 2. So far, so good. I will go ahead and put the coefficients inside. So we're going to get alpha over √2, alpha over √2, plus, now here we get minus 2 beta over √8, minus 2 beta over √8. Okay, and now to add these together, I'm actually going to write these with √8 on the denominator. So I'll multiply the numerator and the denominator by √4, which gives us 2 alpha over √8, 2 alpha over √8, plus minus 2 beta over √8, minus 2 beta over √8. Okay, and then we can go ahead and sum these. So I'll just bring my 1/√8 outside, and we get 2 alpha minus 2 beta. And then on the bottom, it's also 2 alpha minus 2 beta. So let's look at what we have here. We again have two equations. The first one, top elements need to match. So 3/5 should equal 1/√8, 8, 2 alpha minus 2 beta. And then the second one is that minus 4/5 should equal 1/√8, 2 alpha minus 2 beta. Now, you could go ahead and try to solve these using the technique we described earlier, but if you just pause and look for a second, there is something very wrong here. These two things are equal. They're both 1/√8, 2 alpha minus 2 beta, and we're saying they should be equal to 3/5 and minus 4/5 at the same time. So that clearly can't happen. There's no solution for this. And so in this case, it's impossible to write this vector as a linear combination of those two vectors. So one might ask, why were we able to do this with the vectors in the previous slide, but not with the vectors here? And the answer is this thing called linear independence. So linear independence is just the fancy math name for the idea that vectors we sum must be in different directions. So when we had this question, let's go ahead and look at the graphical representation. So same thing as we did before. So here I again have our axes, sorry. This is ket0, this is ket1, and then this is our target vector. But if we look at the two vectors they're asking us to sum, those are those two right there. If you actually work them out, they look like this. And so it's kind of like how we said before, if you just walk along Cedar Street the whole time, you're never going to get to the donut shop. The same thing just happened here. So what we saw on the previous slide, where there was these two equations that couldn't possibly both be true, that's the mathematical version of not being able to reach the donut shop by just walking on Cedar Street. Now, how can you actually tell this with math? Well, some of you might have noticed this, but these two vectors are special because they differ by only a scalar. What do I mean by that? So if I write 1 over root 2, 1, 1, that is actually going to be equal to some scalar, so I'll just call it c, times our second vector. So if you go ahead and work this out, I believe that c just has to be -1, and then this thing will work out. So here, this was 2 over root 8, 1, 1 equals this. And so here you can see, if we just set c equals -1, then these two things are actually equal. And so this is what we use to test for linear independence. If you can write your two vectors as being equal to each other, just multiplied by a scalar, then we say that they are linearly dependent. And if they're linearly dependent, some vectors are going to be impossible to write as a linear combination. So if we have linear dependence, we also obviously have linear independence. And these are typically the ones we like more because you can write any vector as a linear combination or as a sum of those vectors. So all linearly independent vectors is vectors that are not related by a scalar. So let's say that you were asked on an assignment or something, show that 0 and 1 are linearly independent, for example. So how I would do this is I would start off by writing ket0 and ket1, but with a factor in front of one of them. So that c is just any scalar factor. I'll go ahead and substitute in my vectors here. And then I'll bring my constant inside. Now, is there any value of c for which this works? And the answer here is no. You could make c whatever you want, but just as an example, look at the top row. The top row says that 1 equals 0. It doesn't even depend on c. So no matter what you do to c, 1 is never going to be equal to 0. And so we say that these two vectors, 0 and 1, are linearly independent. On the previous slide, we saw an example of what happens when they're linearly dependent. When we got to this stage, there was a value of c that made them equal. If there's no value of c, they're linearly independent. Okay, so all of this discussion aside, this is going to bring us to the idea of span. So the next couple of slides are just going to be me throwing some terms at you. Again, as I said before, please don't be frightened of the terms. They are really simple concepts. So first of all, span. I'll just read out the definition first, and then we'll talk a bit about it. The span, and you typically say the span of two vectors. So for example, the span of ket0 and ket1 is all the vectors that can be written as linear combinations of the given vector set. So again, linear combinations just means sums. And so anything of this form, any vector that can be written as a sum of ket0 and ket1, we say that these are in the span of ket0 and ket1. So the span is kind of like a group. It's a group of vectors. And the way that you figure out whether something is in that group or not is whether you can write it as a linear combination of your two vectors. So graphically, what this looks like is if we go to our XY plane and we draw ket 0 and ket 1, the span is going to be every single vector that is a linear combination of these two. So in this case, that's going to be everything in the 2D plane. All of these examples here are in the span of 0 and 1, and there's infinitely many more. Anything in the 2D plane can be written as a linear combination of 0 and 1. And remember, the reason that is because they are linearly independent. So second term is a vector space. A vector space, again, is just a funny name for a group of vectors. So some examples of vector spaces. One that we've already seen is all of the 2D vectors that lie on the unit circle. That's a vector space. And one thing that we covered in the optional content of one lab was something called the block sphere. And so all vectors on the surface of the block sphere, that's also a vector space. Now, we teach you these terms only because you'll probably see them come up, especially if you take more linear algebra in the future, you'll definitely hear them again. But they really are just mathematical definitions of fairly straightforward concepts. So my recommendation is if you see a problem on the homework, etc., that uses linear independence, linear combination, vector space, span, go back to these slides and just look at what the basic definition of these terms is. If it's asking you to find a vector space, don't get scared. Just remember, a vector space is just a collection of vectors. And so all you're looking for is a group of vectors in that case. Now, all of this discussion about linear combinations and linear independence, vector spaces, this brings us to the third idea from our donut example, which was that there are multiple ways of summing to the same blue vector. So remember, we could have gone up whatever it was, Highland and the side street, or we could have gone Cedar and Elm. There are multiple ways of getting a vector. So what does that look like mathematically? Well, as I just said, we can always ask, is there a way to describe each vector in this space? So again, a vector space is just a group of vectors. Can we describe every vector in that group as a sum of two vectors? In this case, if we're looking at the 2D plane as our example, the answer is yes, right? We just saw, yes, you can. You can describe them all as linear combinations of 0 and 1. So we have a special name for these 0 and 1. We call them a basis for the vector space. And in turn, we will sometimes call them basis vectors. And all that means is that every vector in your space, or again, every vector in some group, can be written as a linear combination, or sum of basis vectors. So again, the common theme with this whole lab is there's just a lot of new terminology, but I really think the basic idea is fairly simple once you wrap your head around it. You're given a group of vectors, you want to know if every vector in that group can be written as the sum of two other vectors. That's really all you're asking with a basis. So I've spent a lot of time talking. Let's go ahead and do an example. Can we find a way to describe each vector in the space as a combination of two vectors? We asked that on the previous slide. Let's do one example. So this 3/5 minus 4/5, that is in our vector space. That is one of the vectors in our group. And we're asking, can you write it as a linear combination of 0 and 1? And we saw in a previous slide, we worked this out, that you can. And the coefficients you get are 3/5 and minus 4/5. So as we said before, these vectors here have a special name. They are called basis vectors. And the way that I like to think about it is they sort of form the mathematical foundation from which you can build any other vector in this space. And the way you build them is just by changing these coefficients. Let's look at another example. Here is a second possible basis for the 2D plane. So just like there were multiple ways of getting to the donut shop, there's multiple bases that will give you every single vector in the vector space. So as an example, right here, we're looking at plus and minus. And we found, again, in a previous slide, that you can do this computation with these coefficients, the minus root 2 over 10 and the 7 root 2 over 10. And again, you could get any vector in the 2D plane just by changing these numbers. And that's why we would call plus and minus another possible choice of basis vectors. And it just so happens that there are actually an infinite number of choices for different bases. So ket 0, ket 1, ket plus, ket minus, we could easily throw something else at you that is a different choice of basis. But as long as we say it's a basis, it means you can always write any vector as a linear combination of those two vectors. Okay, so that was a lot of talking. I've been going for 40 minutes. I'm going to pause for questions, and I'll take more time here for sure to answer them. I know one person asked to go over span more closely. So if you still have questions about span, please feel free to throw them in the chat. But if anybody else has questions about any of the things we've talked about, basis, linear independence, linear combinations, span, vector space, feel free to throw them in the chat. I know that this is probably a lot of terminology that's new getting thrown at you, so no worries if it seems confusing. Okay, so can we do one more linear combination? Here, 1 over root 2 will be a basis vector. Okay, so I'll answer actually the second question first. I'll get back to the example of a linear combination in a moment. So here, just to be clear on my terminology, these two vectors are the basis vectors. So the coefficients aren't really included in this. It's just these two vectors. We know just by changing the coefficients on them, we can get any vector in our space. How do you get root 8 in the denominator from having root 2? Yes, that's a good question. And sorry, I kind of skimmed over that. So what you can do is we started off essentially with 1 over root 2. I'm going to multiply that by root 4 over root 4. Now notice that's the same thing on the numerator and the denominator, so it's just 1, so it doesn't change the value. So what we get is root 4 divided by root 2 root 4. Now we know what the square root of 4 is, that's 2. And then on the bottom here, when you have a product of two square roots like this, you can just write it as the square root of the product. So this turns into the square root of 2 times 4, which is of course root 8. So sorry I went through that quickly, but that was the combination, that was the computation I was doing there. Okay, so for the linear combination example, I'm gonna say that we probably shouldn't right now, just because those examples do take a lot of time to work through. But if it doesn't make sense, I would strongly recommend just watching those same examples again. The ket 0, ket 1 example is admittedly kind of simplistic. It's not that difficult. The ket plus, ket minus example, where we found these two coefficients, that is more like, that's a more difficult question that you might see on the homework. So I guess just to give a brief overview of it though, the general idea was to start off with your state. So whatever state you're given, write it as a linear combination of, in this example, it was ket plus and ket minus. It could be anything else though. Then you substitute in the values of ket plus and ket minus. Like that. Now you use the rules of vector multiplication and addition to write this as a single vector. So what you end up getting here was alpha plus beta over root 2 and alpha minus beta over root 2. And then you set up a system of equations. So you look at the first element of this vector and the first element of whatever your ket psi was. That's going to be your first equation. Then your second equation is going to be the second element of this vector and the second element of whatever ket psi was. And you just set all of them to be equal to each other. With those two equations, you use any technique you want to solve the system of equations. And then you should get answers for your alpha and beta, which you then plug back into this formula, and then you have your linear combination. Somebody asks, would there be a situation where there's a combination of 3 vectors? Yeah, so this is something that we're not going to get into today. But certainly you could imagine a situation where you would have a linear combination of 3 vectors. It works the same way. It would just be a sum of 3 different vectors. The reason we usually deal with a sum of only 2 vectors is because we're in 2-dimensional space here, right? All of our examples are XY coordinate plane, 2 dimensions. And so a handy rule of thumb is if you're in 2-dimensional space, you're usually only going to talk about linear combinations of 2 vectors. You could have a linear combination of more. I'm not sure if that comes up in the homework, but it would just be a sum of 3 different vectors in that case. Okay, cool. So I'm going to move on. Actually, oh, sorry, somebody asked, what will be the coefficients? Right, sorry, so I should mention that. Okay, so what you would eventually have is, if you were doing a linear combination of 3 vectors, I'll just continue on this example to try and show what this would look like. So let's say we had this, and then we have a third thing here, gamma, I don't know, maybe this is ket 0, right? So you're trying to do a linear combination of plus, minus, and ket 0. So here, all of your vectors are still only 2-dimensional. So you'll write out all of your vectors, you'll figure out, you'll do your substitutions with the definitions, right? You'll sum all of them up and you'll get a vector that has some combination of alpha, beta, and gamma in the top and the bottom, right? I don't know what it would be, but it would be some combination of those 3 in your final equation. You would still have 2 equations and you would set them up in the exact same way. But what you would find is that there's not a unique solution for the coefficients. So in all of the examples we've seen so far, we solved for a single value of alpha and a single value of beta. But here, you might get essentially infinite different answers. There would be infinitely many different values of alpha, beta, and gamma that you could pick. And so those are sometimes a bit more difficult to solve. But usually what you'll do is you'll just pick a value of gamma. So you'll be like, okay, I'm just going to say that gamma is equal to 1. And if gamma is equal to 1, then I can go and solve for a unique value of alpha and beta. So I would say that that's probably a more challenging question for sure. But the general machinery is the same. You write it out as a linear combination. You put everything together as a single vector. You set up your system of equations, and then you solve that. And the only difference you would see with 3 vectors is your solution would have infinitely many answers instead of just 1, like we saw before. So I'm sorry if that didn't make sense. I wish I had like a full, an actual example to work through here, but that is the general idea. Okay, so let's move on to the second half of the lab. So eigenvectors and eigenvalues, which by the way is shorter. So I don't think we'll go too far over time here. So what we saw in the previous section is we could write this same vector, this 3/5 minus 4/5 thing, using 2 different bases. So again, bases was just the name we gave to the set of vectors from which we can generate any vector in the group just by changing the coefficients. And so here we saw that we could write the same vector as a linear combination of 2 different bases. And I said that this was kind of the same idea as when we were trying to get to the donut store of walking along 2 different paths, right? There's multiple different ways of getting to the same final vector. But this might be a good time to sit back and ask, hold on, why are we learning so much stuff about different linear combinations and different bases and all this stuff to do with linear algebra and vectors, and why does all of this matter? And so we're going to take a step back here, finally introduce something called eigenvectors and eigenvalues, which is kind of like the main thing that we've been working through throughout all of the past 2 weeks. To do that though, we do have to do a quick review about how you apply a gate to a state. So here I have a usual circuit diagram. We have our matrix definition of the Z gate. And we should remember from previous labs that the way to compute psi out is to multiply Z by psi in. And that's just going to be matrix vector multiplication. So let's go ahead and do that. Here's an example. Let's suppose psi in is that same example we've been seeing before, 3/5 minus 4/5. So to compute this, I'm going to fill in my value for the Z matrix, and then we're going to do matrix vector multiplication. As a reminder of how that works, we start off with the first row of our matrix, and we're going to multiply pairwise with everything in our vector. So that's 1 times 3/5 plus 0 times minus 4/5. Then we move on to the second row of our matrix. So 0 times 3/5 plus minus 1 times minus 4/5. Okay, and then I go and simplify all of this. We should get 3/5, 4/5 as the answer. So that's how we would usually figure out the effect of a gate on a particular state. So I'm going to go ahead and give everyone here a chance to review that same machinery. So I'm asking you to find Z times this, which is just Z ket 0, and Z times this, which is Z ket 1. So go ahead, do the same matrix multiplication. I'll throw up a poll here on the screen for people to answer, and then I will go over the problem in just a few moments once everybody's had a chance to answer. Okay, so about half of you have filled in your answers. I'm going to start solving this problem. So again, the key here is just to use matrix vector multiplication, just like I said on the previous slide. So in this example, we'll start off with this. I'll start off with the first row, and then we just multiply pairwise with our vector. So this is going to be 1 times 1 plus 0 times 0. I'm done the first row, so I move on to the second row. Here we're going to have 0 times 1 plus minus 1 times 0. Work all of this out, and we should get the answer 1, 0, which of course is just ket 0. Just like that. And so I guess just to summarize here, what we've done is we have Z ket 0 equals ket 0, which if you just take a step back from the math we're doing for a second, this is kind of interesting. It means whenever you have this matrix times this particular vector, the matrix just disappears, which is awesome if you're trying to simplify some math expression. Okay, let's go on to the second example. I'll do the same thing, start off with the first row, multiply pairwise, so 1 times 0 plus 0 times 1. Move on to the second row. And here we have 0 times 0 plus minus 1 times 1. Carry out all of that math, and we should get 0 minus 1. So this is just equal to minus 0, 1. I can pull out the minus sign. And then that is minus ket 1. So again, just to summarize what I did here, we have Z ket 1 But now, instead of just Z disappearing, we get this minus sign popping in, like that. But again, both of the right-hand side of these expressions, they're way nicer because they don't have any matrices in them. And honestly, matrices are kind of a pain to work with, as we have seen in the past. Okay, so let's move on. This is what we just computed in that previous section. And this is how we're going to introduce eigenvalues and eigenvectors. So again, these are kind of weird terms. And I have to admit, eigenvalues and eigenvectors have kind of a reputation, even in university, of being kind of hard to understand. But really, it's a simple concept with a complicated name. So whenever you have something of the form Z times some matrix equals coefficient times the same matrix, you have an eigenvalue and an eigenvector. So these vectors here are called eigenvectors for the Z gate. And then the coefficients are called the eigenvalues. That's all there is to this. Now, again, just to summarize, what we saw here was that Z ket 0 equals ket 0, and Z ket 1 equals minus ket 1. And so basically, whenever you have an equation where there's a matrix on one side and no matrix on the other side, you have an eigenvector and an eigenvalue of that matrix. So key takeaway here, to find if you're asked whether a given vector is an eigenvector of a matrix, just multiply the vector with the matrix and check to see if the matrix disappears. Okay, so why use eigenvectors and eigenvalues in the first place? Let's return to this example where we're trying to find Z times our 3/5 minus 4/5 state. So I'm going to go ahead and write this in our bracket notation. So we saw that this 3/5 minus 4/5, it can be written as a linear combination of ket 0 and ket 1. Just like that. And now all I'm going to do is I'm going to distribute into this. So we end up with 3/5 Z ket 0 minus 4/5 Z ket 1. And now you might recognize we've already figured out what these things are. We know that those vectors are eigenvectors of the Z gate. And so we can just get rid of the matrix. So here we end up with 3/5 ket 0. Here we end up with minus 4/5. This one was minus ket 1. The minus signs cancel out. So we end up with 3/5 ket 0 plus 4/5 ket 1, which is the same thing that we got when we did matrix vector multiplication up here. Notice though, in this calculation, we never did matrix vector multiplication. We just sort of distributed in, noticed that we had these eigenvectors, and then we were able to solve the problem anyway. So the reason eigenvectors and eigenvalues are so important is that it makes math with matrices look like math with regular numbers, right? In here, we never wrote a vector, we never wrote a matrix. We were able to solve everything without matrix vector multiplication, which is super, super powerful. So the key takeaway here is that applying a gate to a qubit, or multiplying a matrix by a vector, is really easy if you can write the vector as a linear combination of the eigenvectors of the gate. So that's a bit of a mouthful, but all that meant here was writing our vector as a linear combination of the eigenvectors of Z, which were 0 and 1. So there's a quick analogy that I will go over here, which is a little bit silly at first glance, but I promise it makes sense. So think about a car. We can start off with your standard definition of a car. It's got 4 wheels. I'll just draw it in 2 dimensions here, but it's got 4 wheels, it's got a body, and it's got an engine. And if you really use your imagination for a second, if we wanted to write this as a linear combination, a sum of its parts, we could write something like this, right? Car number 1 is 4 wheels plus this shape of body and this shape of engine, right? Again, we're just writing things as a sum of parts. But if we look at, say, a second car that looks like this, we can write it as a sum of the same parts. So again, this was the idea of a basis. You could write any vector, any car, as a sum of these parts. So to summarize, we know how to work with wheels, engines, and bodies, and we can combine them in different ways to make different cars. The same idea applies with eigenvectors. If we know how a particular matrix behaves on our eigenvectors, we can combine them in different ways to make different qubit states, and we still know how the gate operates on that qubit state. So I know that we're at 8:30 here, but I just have one more example, which hopefully will make this idea a lot clearer. Now, we'll start off with a zoom poll here. This one is just standard matrix vector multiplication. So just like last time, we're going to start off with sort of like the inefficient way to do this, and then we'll go ahead and look at how to do it with eigenvectors and eigenvalues. So again, use this as an example to practice matrix vector multiplication. I'll throw up a zoom poll right now and enter in your answer when you go ahead and get it. Okay, so it looks like just about half of you have filled in your answers, so I'll get started on my solution. So here, like I said before, we're just doing standard matrix vector multiplication. So I'll start off with my first row to get the first row of my answer. 0 times 1 over root 2 plus 1 times 1 over root 2. Done with that one, move on to the second row. Here we have 1 times 1 over root 2 plus 0 times 1 over root 2. Okay, now if I work all of that out, I should get back to 1 over root 2, 1 over root 2. And so if you remember the definition, I guess maybe that was the hard part of this, but that is exactly equal to ket plus, which should have been the answer for this question. So you might see here again, essentially what we've ended up with, x times ket plus, that's what we started with, is equal to just ket plus. Very similar idea to what we just saw with the Z gate, where we have an equation and the matrix is just gone on the other side, right? The same vector on both sides, but the matrix is now gone. So you might guess correctly that ket plus is an eigenvector for the X gate. Now, here's just a summary of what we saw. We did the first problem up here. And essentially what we saw is that X ket plus is equal to ket plus. You could do a similar example. We won't do it here, but X ket minus is equal to minus ket minus, which I know that's kind of confusing, but hopefully it's clear what that means. It's just a minus sign in front of our usual vector ket minus. And so because we have equations where the same vector appears on both sides and the matrix has disappeared, we call these things eigenvalues and eigenvectors. Okay, so let's return to an example we did before where we want to do matrix vector multiplication. But again, we have a trick up our sleeves this time. We know how to write this state as a linear combination of the eigenvectors of the X gate. So again, the eigenvectors of the X gate are ket plus and ket minus. And so we know that X times that gate is equal to x times, now I'm just looking back at our previous slide for what these crazy coefficients were, but it was something like this. So again, this is just an example we did in previous slides, figuring out how to write something as a linear combination of two vectors. But these two vectors are special because they're eigenvectors of x. So now we can do a trick. We can distribute the x inside these brackets. So we get minus root 2 over 10 x plus 7 root 2 over 10 x minus. And then we know what happens to these vectors when we operate with x on them. So this becomes minus root 2 over 10. This one was just ket plus 7 root 2 over 10. This one turned into minus ket minus. And so again, I'll just bring that minus sign out, and we already have our final answer. Again, we found this without doing any matrix vector multiplication. And this is the power of eigenvalues and eigenvectors. So again, just to emphasize here, the key takeaway is that applying a gate to a qubit is really easy if you can write the vector as a linear combination of the eigenvectors of that gate, which again just means going from this, the initial vector, to a sum of these two special vectors called eigenvectors. So this is this eigenvector and eigenvalue stuff, and basically the problem I just showed you here, where you can do linear algebra without ever writing down a vector or a matrix. That's why we care so much about linear combinations and bases and all that kind of stuff, because they all tie back to using eigenvectors and eigenvalues to evaluate quantum gates. And we're going to see that come up a lot next semester. Okay, so I'm going to go through some just sort of a summary of today's lesson before I have one last word after this, and then we'll go to questions. So a vector space, this was just a term for a collection or a group of vectors. A given qubit state in a vector space can be expressed as a combination of two or more states in the space. So this little or more here is what one student had asked. Could you do a linear combination with 3 vectors, for example? Linear independence was the idea that, well, if you had 2 vectors, you could check whether they are linearly independent if the states cannot themselves be written as combinations of one another. So the easiest way to see that was just whether they could be written as, you set them equal to each other with a scalar in front of one of them. And then we had the idea of a basis, which is just that these states can be combined to express every other state in the vector space. So all you do is you change the coefficients, but the vectors stay the same, and those vectors are called a basis. Then we talked about eigenvalues and eigenvectors, and we saw that applying a gate to its eigenvector results in the same vector times a constant, where the constant is called the eigenvalue. And that's really helpful because it gets rid of the matrix in a very straightforward way. And applying a gate to any other vector can be turned into a problem of applying the gate to the eigenvectors by breaking your vector into a linear combination of eigenvectors. So that's what we have there. So hopefully some of this starts to bring together all of these ideas in a way that makes a little bit more sense. So my final word before going to questions is just to briefly address, why all of the math? Why are we talking about this in the first place? Aren't we supposed to be working with physical devices called quantum computers? And the answer is yes, but a physical computer, as we talked about, I think 1 or 2 weeks ago, it uses currents and magnetic fields to control the quantum computer. And then as output, we also get currents and magnetic fields. All the math that we're learning is basically just our attempt at describing the physics of this system. So why are we using vectors for qubits? Simply because they can't be described by a single current or a magnetic field. They're a combination of multiple things. So why use matrices? Well, matrices are just things that operate on vectors. So all of the math here, even though it's super theoretical, I know we've spent this whole semester basically with me writing math on a tablet, but all of these things are representations of what goes on in the real world. So with that, I know we have gone a little bit over time, so I do apologize for that. But I'm happy to stay behind and answer a couple of questions if you have them. So anything on the first part of the lab or the second part to do with eigenvalues and eigenvectors, go ahead and throw those questions in the chat. Okay, so why do we multiply gates to the 0 or 1? Why not do the opposite? Yeah, that's a good question. So I think what you're asking here is, why do we do something like this instead of this kind of idea? Is that right? Okay. So I think the simplest answer to this is just to say that's how quantum mechanics tells us it should be done. So if that's all you understand, that's okay. But to go into a little bit more depth here, the reason again comes back to dimensions of matrices. And remember, we had that rule for multiplying matrices and vectors where the inner dimensions had to match. So if I write out what the dimensions of these things are, our X matrix is a 2 by 2 matrix. And our 0 vector has 2 rows and only 1 column, right? So it's a 2 by 1. So we can do this multiplication because the middle 2 dimensions match. So that looks good. What happens if we try the same thing in this order? Well, here we still have a 2 by 1, and X is still a 2 by 2 matrix, but now the inner dimensions don't match. And so there's no way of doing this computation. So the real reason we do it in this order is just to make sure that the dimensions match in our matrices and vectors. Okay, so somebody asks, is ket plus an eigenvector? And the answer is yes, but I would add a little bit onto that. It's an eigenvector for the X gate. So how do we tell it's an eigenvector? Because when you apply the X gate to it, which is just this, you get back the same vector on the other side, right? But ket plus, for example, is not an eigenvector for, say, the Z gate. So if we did Z of ket plus, we would get, I think in this case, you actually get ket minus. So basically, though, it's no longer the same vector on both sides. And so ket plus is not an eigenvector for Z, but it is an eigenvector for X. So somebody says, I feel confused on X. Is it a separate gate? Also, in the previous questions, what were we trying to solve for if X is a gate? Yes, great question. So X is a gate here. And if you remember the definition of X, so all of our gates could be represented by matrices. Our X gate was represented by this matrix. And so yes, X is a gate. And so what we were trying to solve for in the previous questions was, if you started with a state, so I'll draw a circuit diagram actually. So if we started in the state, remember this 3/5 minus 4/5 thing that we were playing with for all of today, basically. If you started in that state and fed it into an X gate, what would you get on the other end? That's the question we're asking. And the mathematical way of saying that is, if you start with 3/5 minus 4/5 and you apply the X gate. So remember, it's a little bit confusing because it's almost like a mirror image from the circuit, but applying the X gate goes on the left. So if you apply the X gate to this, what do you get? That was the question that we're trying to answer. Hopefully that's helpful. And feel free to send follow-ups here if you'd like as well. Can an eigenvalue be an imaginary number? Yes. Yeah, eigenvalues can be imaginary or real or complex. Absolutely. Yeah. Okay, so somebody asks, the matrix of C naught in IBM quantum experience is different than the matrix given on other sites. So I'm not going to touch on IBM quantum experience right now, but feel free to post that question on Piazza. There is an interesting answer behind that question. Okay, please explain how to interpret the first statement that you wrote on the slide, why use eigenvectors? Okay, let's go back to that. Oh, I have to go through all these. Sorry, I don't quite remember. Oh, this one. Is this the one that you're referring to here? Yes. Okay, cool. And so the first statement, the first statement that I wrote. Okay. So all that I've done here, going from this question being asked, honestly, for this example, you can kind of just ignore that. All that we really care about here is Z times this vector. The first step here, I mean, I did it very quickly because we did it in a previous slide, but in reality, this step can take quite a while, right? This is basically figuring out how you write 3/5 minus 4/5 as a linear combination of ket 0 and ket 1. And so after we did that exercise, we had an equation that looked like this. So that was our final answer. And so literally all I'm doing here is substituting in this 3/5 minus 4/5 for the right-hand side of that equation. And so that's what we get there. Okay, so in the previous questions, there was a 1, 0, 0, 1 matrix and a 3/5 minus 4/5 vector equal to the x and the vector. What were we doing in that question? Okay, so let me go back to that section. I should have just done this originally. Okay, so I guess you're talking about this one. There was a 1, 0, 0, 0, 1 matrix. Okay, I'm not quite sure what that question is referring to. I'm sorry. Oh, okay. Cool. All right, so hopefully I helped some people understand. Once again, I totally understand that this lab in particular, honestly, I looked at the slides and I thought this was going to be quite a lot of content. So no worries if you have to go back and rewatch parts of this. I hope that I've gone, slow enough and been deliberate enough that some of this stuff will make sense on maybe like the second or third time that you watch it. Okay, so let me zoom through all of this. Okay, cool. So again, yeah, my apologies for going over time, but I am going to throw the post-lab feedback up just to see how people are feeling now that we've spent an hour and 45 minutes talking about all this stuff. Hopefully I've cleared up some misconceptions or any doubts that you had. Awesome. All right. Well, thank you everybody for bearing with me and sticking until the end of a rather long lab session. If you still have the energy, I am going to spend about 10 more minutes talking about the research that I do in my regular day job. And if you're curious about that and how it connects to all of the stuff we've talked about today, feel free to stick around. Like I said, it shouldn't take more than 10 minutes. But as always, you're more than welcome to drop off. That's the end of the required content. You should be good to do the homework with all the stuff we covered here. Certainly the stuff I'm about to cover is not going to show up on the homework. So don't worry about missing anything. I'll pause for about 30 seconds before I start the optional content, but to all of you heading off, have a great break. I look forward to seeing you back in semester 2, and good luck with the homework this week. So I'll stick around another 30 seconds or so until we get started with the optional content. Okay, so let's get started with optional content. Now, like I said, this stuff is actually, it's going to be different for every single TA, because basically what we're doing this week is we just gave each TA 10 minutes to talk about their own research for any students that are interested in, what are the topics that are actually being researched right now. And also, of course, we're happy to answer questions if you do have any. One thing that I have learned is the best way to get a researcher to talk is just to ask them about their research. They will talk for hours at you if you just ask about their research. So this is what I do. I work on something called quantum compilation. And to explain what that is, I'm going to go back to a diagram we saw last week. So this diagram, we originally had it to explain why we were learning Python in the first place. And the reason we were learning Python is that us as the programmer sitting over here, the way that we interact with a quantum computer is we write out some Python code. The Python code gets fed into an interpreter. And I said that this interpreter was written by IBM, so we didn't really have to worry about it. And the interpreter translates your code into electrical and magnetic signals for the quantum computer. Then the quantum computer sends a bunch of electrical and magnetic signals back. It gets translated back by IBM and fed back to you as the programmer. So what we're focusing on in this course is essentially the code. All of the math that we're learning, all of the programming that we'll do in the second semester is all the code here that gets fed into the interpreter. My work is on the interpreter itself. So researching how we make this happen. How do we go from code that a quantum programmer writes and translate it into electrical and magnetic signals for a quantum computer? So let's zoom into this a little bit. Again, we're starting off here on the left with some code from the programmer being fed into our interpreter. And at the end of the day, we want to spit out some electrical and magnetic signals for the quantum computer. And so the question becomes, okay, how do you do this huge translation in the middle? And it's actually a lot more straightforward, at least at first, than you might think. So we haven't quite gotten here yet with the programming, but when you start programming in Qiskit using Python, which we'll do in the second semester, you'll see that in the code, they use these same terms for matrices that we've been looking at this whole time. They have an X gate, they have a Z gate, they have an H gate, they have like 500 other gates too, and all of them are defined using matrices. So inside the interpreter, when I receive your code, essentially what I'm getting is a whole string of matrices to apply to a particular vector. And the question then is, okay, we have all of these like abstract mathematical objects. How do we get a quantum computer to effectively do all of this matrix multiplication for us? Now, we can use some knowledge of physics, which I am not a physicist, by the way, I'm a computer scientist. And so physicists will go out and they will tell you what matrices a quantum computer can do natively. So what do I mean by that? When a quantum computer operates, you send in certain electrical and magnetic signals. Those electrical and magnetic signals will produce a certain matrix. But this matrix looks a lot more complicated than the ones we've seen so far. So just as one example, it might look something like this. So here we have a very messy looking expression. And you might notice this is not even a matrix because this is actually just the top left element of a massive matrix that has lots of other ugly stuff off to the side of it. And this is what we call a native operation for a quantum computer. Now, what we have here, you might notice there's some variables. So we have this variable tau, we have a variable delta, we have another one omega. And basically each of these things corresponds to an actual knob, effectively, like some kind of control on the quantum computer. So each of these things is kind of like a dial that you can spin and tune in different ways. And these things are the values that actually dictate, how much of an electric signal are you shooting out? How much of a magnetic signal are you shooting out? All of those are encapsulated in these variables. And depending on how much of an electric or magnetic field you're sending out, you will get different values for this massive matrix. So instead of trying to get somebody to program using a matrix that looks like this, we quite reasonably ask them to program using these simpler matrices. But somebody still has to take care of the problem of how do you translate now from matrices that look like this to matrices that look like this. Sorry, that was a really ugly arrow. Let's try that again. There we go. How do we do that translation? And the short answer is that, at the end of the day, we just have this big formula with a bunch of variables in each corner of our matrix. And so if we want to create an X gate, for example, we would just have a huge equation in each of these 4 spots, and we could line them up. We could say top left has to equal top left, top right has to equal top right, and so on. And we end up with a system of 4 equations, 3 variables. We can go ahead, try and solve it, and we'll get whatever we need for those tau, delta, and omega variables. Now, this is straightforward in this case because we're only looking at 1-qubit gates. And it turns out that whenever you're using a 1-qubit gate, which so far that's all we've used, you can always find a solution just by doing some, well, maybe not so basic, but you can find a solution just by solving this system of 4 equations. Things get a bit more complicated though when you go to 2 qubits. So I'm not going to go into that right now, but once you step up to 2-qubit gates, sometimes you will have gates that you cannot implement, you cannot equal with a matrix that looks like this. No matter how you turn those dials, you'll never get something that equals what you want. And so what you have to do instead is you have to string multiple of these native operations together. Just like we saw stringing an X and a Z gate together, you can string these native operations together to get yourself more and more complicated gates. And the question becomes, what is the simplest way to implement a certain 2-qubit gate? Which ways are the fastest to execute on the computer? Which ways are most robust to error? Which ways fail least often? So there's all of these questions now about how you construct 2-qubit gates from these native operations for the quantum computer and these dials that you have to turn, which is ultimately what you're feeding into the machine. And so this is what I research. This is the stuff that I think about every day. And it's a very interesting problem that is heavily based in math and computer science. And I think the coolest part about this though is even if the details of it don't make perfect sense, I hope that the idea here is at least clear, that you have sort of these 2 gates. You have a simple one that the programmer uses, and you have a complicated one that the quantum computer understands. To match them, you're just solving a system of equations sometimes, but when you go up to 2 qubits, the system becomes much larger. Sometimes it doesn't have solutions, so you have to add more native operations, all that kind of stuff. And it's an active area of research. The question of how you compile code to hardware is still very much an open question that we do not know the answer to, and frankly, are not really close to knowing the answer to. So there's a lot more exciting research to be done here. So hopefully that was at least a little bit interesting to go into a bit more detail on what I do. With that though, I'm going to wrap up today's lab session. That's the end of the optional content. Once again, all of us will be available on Piazza if you do have any other questions that we didn't get to today. Other than that though, this is the last lab before the break. So I hope you all have a lovely break. I hope you have a great rest over that time. Celebrate when you can, and come back fresh to start again in the new year when we get into more quantum computing. So thank you all for being an awesome audience. Have a great break, and good luck as always on the homework. We'll see you in the new year. Bye.